So let's try to finish the proof. I will actually need to add one more arrow, which is from 3 to 4. Okay, let me write it here, 3 to 4. And this is immediate because by the fact that a continuous function is measurable. So 3 is for bounded measurable functions, 4 is for bounded continuous functions. So if you believe in the fact that continuous functions are also measurable, then 3 implies 4 is immediate, okay? So assume that expected value of e to negative rx is given as e to negative rx nu dx for every r. Okay, so I don't like this expectation too much in this proof. So I want to replace it by an integral with respect to some other measure, which is the distribution of x. So here nu is not necessarily the distribution of x. Okay, it is an arbitrary measure satisfying this property. But on the other hand, I can always write it in terms of an integral with respect to the distribution. So let nu x, I'm going to denote it by nu x to distinguish it from this nu, be the distribution of x. So we have, or we assume what? We assume that this integral with respect to nu is equal to the same integral, but with respect to nu x. Okay, with respect to nu x. R bar plus for every r. Okay, and okay. So this is what we assume, and we want to show that f d nu is f d nu x for every bounded continuous f. This is what we would like to show. So let's have a look at this integral, okay? Note that, so we have this e to negative rx nu dx over r bar plus. So I can see it as e to negative x to power n, okay, nu dx. And this is like I have my outcome is x. So the random experiment is done on the positive real line. Okay? And e to negative x is my random variable. So it's a function of an outcome. And the last thing, raised to power n, is a function of the random variable. And nu is the measure on the outcome space, the probability space, the probability measure, the underlying probability measure. So this is like some random variable raised to power n. Raised to power r or n. I should have written n. Okay, so note that taking r equals n, we have this. So now I'm taking n to be an integer. So this is like e to negative x is the random variable, and we're raising it to power n. What we can do is to make a change of variables by using this change of variables theorem. So use the change of variables theorem to write it as y to power n. So this is as if we're making this change of variable, e to negative x is y. And now this is going to be what? This is going to be e to negative x function is in dy. I'm going to denote it by, so this is the image measure of this random variable, right? So I'm going to denote it as nu of negative logarithm, because this is like the inverse of this function, right? This is indeed the inverse of this function. Okay? So this is the measure defined by, so nu of negative log at some set A is defined as nu of the set of x's whose exponential functions take value in A. Okay? So this A is a subset of 0, 1. A Borel subset of 0, 1. It's the image measure. So remember this change of variables theorem from last week. Just the way of looking at this is a bit different in this context. In this integral, x is your omega, e to negative x is your capital X, the random variable, and power to n is your function f. So this is like expected value of f of x, okay? But this capital X is not this x. It is more like the y, okay? So now that's an integral over 0, 1. Because if you look at this function, so your x is in this scale, x is in r bar plus, whereas your y is between 0 and 1. You either take the exponential function, or from y to x you take the negative logarithm. So do the same for the other integral, namely the integral with nu x, to get this 0, 1 y to n nu negative log measure dy, y to n nu x negative log measure dy, 0 to 1. So for all n, for all n. So we did a change of variables. Well, I have it for power 1, power 2, power 3. I have it for all powers. And I can just multiply those integrals by constants. And using linearity of integral, I can generalize this to all polynomials. So since the integral is linear, this generalizes to all polynomials of all degrees p, okay, on 0, 1. So p of y nu negative log dy p of y nu x negative log dy. Well, I told you this is the core of the proof, so it's not very trivial. You see? Okay. So the next step is actually going to be through a famous theorem from analysis, the so-called Stone-Weierstrass theorem. This says the following. On an interval like 0, 1, on a closed interval, finite closed interval, bounded closed interval, like 0, 1, give me one bounded continuous function. Well, just continuous function. It is automatically bounded on that interval. Anyway, give me a continuous function. I can approximate it uniformly by polynomials. And there are other versions of this theorem that does not use polynomials, but maybe exponential functions, maybe trigonometric functions. So that's why those functions are used a lot. So exponential functions, polynomials, trigonometric functions. They're kind of dense in the space of all continuous functions. And the sense of this density is that you can find a sequence of polynomials converging to any continuous function uniformly. I'm going to write it formally, okay? So the question is, can we pass from polynomials to arbitrary continuous functions on 0, 1, okay? So the answer is yes by Stone-Weierstrass theorem. Okay, here's the statement. So let G be a function from 0, 1 to R, be a continuous function. Then there exists a sequence Pn of polynomials such that Pn converges to G uniformly, meaning that, well, you look at the difference between Pn and G on the entire interval 0, 1. This is your notion of distance, and this converges to 0. This is the meaning of uniform convergence. So you can approximate G by Pn's polynomials. In particular, we have pointwise convergence. Pny converges to G of y for each y. So we already have Pny nu negative log dy equals Pny nu x minus logarithm dy. So can we say that these integrals converge to the limit function, the integral of the limit function? All integrals are over 0, 1. So all we have to do is to justify that we can take the limit. So G is continuous function. Pn is a polynomial for each n, okay? They are defined on 0 to 1 interval, okay? So the theorem we'd like to use is which limit theorem? Which limit theorem should we use? We have two, right? Monotone convergence theorem and dominated convergence theorem. Fatou's lemma, it doesn't work here. We have the limits. We want the limits. So either mon or dom. Which one? Choose one, and we'll try to show that we can use it. Dominated, right? We don't have monotonicity here. This theorem doesn't give us any monotonicity. It doesn't say anything. So let's try to focus on. So let's justify that we can take this limit using, I'm going to say, bounded convergence theorem, the special case of dominated convergence theorem, where the dominating random variable is a constant. So let's do it. So the claim is that Pn is a dominated family, is dominated by a constant. So the proof of claim. So first, Pn and G are continuous on 0, 1. So they are also bounded. They are also bounded. Okay. Let me write P1, P2, etc. as well as G. So they are all continuous functions, therefore they are bounded. Okay? I'm saying it only on the interval 0, 1. Okay? Of course, on the real line, you can have a continuous function which is unbounded, right? Exploding to infinities. But on 0, 1, it's fine. Okay, so here's what we want to do. So Pn of y, okay, what is that? Pn of y minus g of y plus g of y. So I can write it as Pn of y minus g of y plus g of y. Okay. These are not necessarily positive, so let me put those absolute values, okay? First, I can bound the second part very easily. This is a finite number, right? G is bounded. Let's try to do it here as well. Sup over y and sup over n. And hopefully this is going to be a finite number. Okay? If we can show that this is a finite number, then we are done, because for every n, for every y, we have a universal bound. Okay? So since Pn converges to G uniformly for some fixed epsilon, so I'm going to use the calculus definition of limit. So this goes to 0, right? I'm just going to use this star. Okay, let's put a star here. So by star, there is some capital N for which this inside the box sup is less than epsilon for all n after capital N. So if you look at this sup, if you look at the sup, So this sup can be seen as the first, the second, the third, up to the nth, the capital Nth, and then things after capital N, which are always less than epsilon. So this is the maximum of the first sup, P1, up to the nth sup, capital N, and then the sups over n greater than n. So this is from 1 to infinity, the first, the second, the nth, n plus first, n plus second, n plus third, they are all here. So they are all less than epsilon. And that's a finite number. A finite number, say C1. That's also a finite number. Say C capital N. Why they are finite numbers? Because this is less than P1y plus G of y, which are bounded. So sup y. So this is indeed less equal max of C1 to C capital N and epsilon, which is finite. So just call it a capital C. Now this capital C is your bound on this sup. So everything is bounded by some constant. So Pny is less equal C plus sup G for all n and y. So Pn, the sequence is dominated, is bounded. So bounded convergence theorem can be used. We're almost done. We're almost done. That's a long proof. But I wanted to really show you that Laplace transform determines the distribution. So I chose not to skip this proof because it's an important one and usually not shown a lot in some textbooks. So what did we show? What did we show? Well, let's look at it. We showed this. We showed this. Okay? So let's write it. So far, we have g of y nu negative log dy equals g of y nu negative log dy. Now this is nu x. For all g on 0, 1, that is continuous and therefore bounded. Okay. So how did we get into this interval 0, 1? We did a change of variables. But our original framework doesn't have 0 to 1. So we should switch back to our original framework, okay? Let's switch back to our original framework. Let's switch back from 0, 1 to r bar plus. Well, we're just gonna take this part and make it e to negative x again. So using the change of variables theorem, gives what? G of e to negative x nu dx, now it's nu dx, equals g of e to negative x nu x dx. So now it's over r bar plus. We're just back to our original case. So all we need to show is that I can replace it with just f of x. For all bounded continuous. Now I have to say bounded because f is defined on r bar plus. Okay. Well, let's just take one. Let f be bounded continuous. Okay. So can I write it in the form g of e to negative x? So if I can see f of x as g of e to negative x, we are done. So let's try to see it this way. So I want e to negative x, but my function doesn't have it. So what can I do? I can just apply negative log, right? Just f of x is equal to this, right? F of x is equal to log of exponential of x because they're inverse functions. So I can, of course, do it. Can I call it g? Can I call it g? Okay, of course I can. But now is g a function that is continuous? So is g continuous? The answer is yes. Well, why not? F is continuous. Negative log is continuous. So g is continuous. Of course, you can be more rigorous, but let me draw a picture. So these are values between 0 and 1. Okay? These are values between 0 and 1. I apply negative log. What is negative log of 1? It is 0. What is log of 0? Well, it is kind of minus infinity. So it's a function like this. And its value at 0 is really plus infinity. Okay? So this is the negative log function. Here I have my y values, which are e to negative x values. And here I have my negative log values. Negative log values. So these are negative log values are just positive quantities, including plus infinity. So now I'm going to apply f to them. F to the negative log values. Well, f is just a bounded continuous function, right? Something like this. So this is f, but I look at it like this, okay? So the values, the inputs are here, the outputs are here. So it's a bounded function. Bounded continuous. Even at infinity, it is still below this bound. So the composition of f and negative log is again bounded continuous. So yes, g is continuous. Therefore, we can apply this result to conclude that we have this. So the result holds. Let me put a double star. The result, double star, holds. And since the distribution of x is nu x, we have e of f of x is given by, so this is expected value of f of x, and the other one is just f d nu for f bounded continuous. End of proof. Well, it took a lot of time, but that was an important result. So at least we all know a proof of it now. So if you're familiar with, if you remember convergence concepts, I mean, there are a couple of nice ideas here. But if you're still learning about convergence concepts in other courses, you can wait for a while and come back to this proof in a later stage, okay? It is not crucial that you understand every single step of this proof. For sure, it is one of the advanced proofs in the course. But I think you can wait for a while to maybe digest the continuity concepts in other courses, like IE 500, and then come back to this proof at a later stage, okay? But in this course, we're mostly going to be users of Laplace transforms, okay? We need to calculate Laplace transforms, and just like generating functions, Laplace transforms determine the distribution, as we just proved, and this means you can just create a table of well-known Laplace transforms, or Laplace transforms of well-known distributions. So again, if you have a positive random variable and somebody asked you to show it has some certain distribution, what you can do is to calculate its Laplace transform, and then look at a list of Laplace transforms and identify it with its distribution. Okay? Yeah. So for instance, we calculated the Laplace transform of exponential distribution. It was C over C plus R. So if you figured that this is your Laplace transform, make sure it has the exponential distribution. Yes?
Do we know something about the convergence of P?
Yes. So Pn not only converges to G uniformly, but also pointwise. So this is just usual convergence, right? For every y, as n tends to infinity, this goes to G of y. But what the Stone-Weierstrass theorem gives us is even stronger. It is uniform convergence. And the meaning of the word uniform is due to the fact that we have a supremum. So not only Pn y minus G of y, limit n goes to infinity, is 0. So not only this, but also single star. Not just for every y we have this converging to 0, but also the supremum over all y's converge to 0 as n tends to infinity. So it's a stronger notion of convergence. Exactly, because this is a main assumption in the theorem. For instance, if you want to have a similar result on R bar plus for functions defined on the real line or R bar plus, you don't have Stone-Weierstrass theorem. So this, for this uniform approximation, you need to have a compact interval, an interval like 0 to 1. Exactly, it can be 5 to 9. For us, we just use 0 to 1, but for any interval a to b that is closed with square brackets, it works. It works. And the idea is that when you take supremum over an interval like this, 0 to 1 or 5 to 9, you have this number being finite. Okay? And it is even like a notion of distance between Pn and G, okay? Like a metric or a norm. If you take 0 to infinity, for instance, this can become just plus infinity, okay? And you cannot call it the distance between Pn and G. So the finiteness is crucial, and therefore you need to focus on an interval, finite, bounded interval, closed and bounded interval. Okay, any other questions? Okay, so there is a last transform I'd like to discuss with you, and it is the Fourier transform. Okay, so this Laplace transform works well with positive random variables. If you like to work with arbitrary real-valued random variables, this might give you plus infinity values, the Laplace transform. So you use Fourier transforms instead. Number 1, generating functions. Number 2, Laplace transforms. Number 3, Fourier transforms. Okay, so now we're going to assume x is real valued. Okay. So now, if you exponentiate, it's no longer between 0 and 1, right? If you look at e to negative r times x, and x takes a negative value, e to negative r times x is not necessarily between 0 and 1. So e to negative rx is no longer in 0, 1 in general. So do you know a function that is universally less than 1? Universally between minus and 1? Sine, cosine. Trigonometric functions. Of course, not tangent. But sine and cosine are always between minus and plus 1. So the idea behind Fourier transform is sine and cosine. Well, more like e to I rx. Do you remember this function from a homework? So that's a complex valued function, right? But its definition is this. Cosine r of x. So that's the real part, and that's the imaginary part. So cosine and sine are always between minus and plus 1. So their expectations are also finite. So expected value of e to I rx, so as a function of r, okay. Now I take r from the real line, not necessarily positive things. And this is a complex number, complex numbers, whose norms are less than 1. What is the norm of a complex number? Well, just the square root of the square of the real part and the square of the imaginary part. So on a picture, okay, so that is the unit ball in the complex plane. So if you look at e to I rx, which is cosine rx plus I sine rx, well, cosine square plus sine square is always 1. So it is always a point on this unit ball. So note that cosine square plus sine square is 1. So the norm of this point at some fixed omega is always 1. Therefore, it is always on the unit ball. Or should I call it sphere? Right? Unit sphere. I'm talking about the boundary. Okay? But so this is for omega 1, let's say. There is omega 2, for which it takes the value here. And there is omega 3. So when you take the expected value, when you multiply them with probabilities and add those values, you will get a complex number, maybe somewhere here. So the expected value is not necessarily on the boundary. It can be inside. Right? So if it's a finite probability space with just 3 values, so you're going to take some kind of a combination, convex combination of those points, and maybe you will end up here. Okay? So it's in this unit ball. Anyway, so no matter what your random variable is, you always have a finite complex number. I mean a complex number which is well defined. Because the cosine and sine are always bounded functions, so the expected values are always between minus and plus 1. So you have, at the end of the day, your Fourier transform is well defined. So this r to e, expected value e to IRX, is called the Fourier transform of, well, the formal vocabulary is that it's the Fourier transform of the distribution of x. And if you like to say it is the something of x, you say it's the characteristic function or the characteristic function of x. So that's also a frequently used vocabulary. Characteristic function or Fourier transform. Fourier transform of the distribution, but characteristic function of x. But if you say Fourier transform of x, of course, we know what we're talking about. For instance, if you have Gaussian AB, the Fourier transform of this has a very nice form, e to I AR minus 1/2 BR squared for every r. So this is also a homework exercise. It's more like an exercise. So what you need to do is to look at cosine of r times x and sine of r times x and calculate the expected values. So it's not a trivial exercise. But there are easier methods of calculating it, which we're not going to discuss in this course, using complex integration. Okay, we're not going to do any complex integration in this course. So if you, I actually put some parts A, B, C, D, E, which really prepare you for this end result. So you just need to go through certain steps, and then the final result will be this. So it is not like a one-shot calculation, but more like you need to follow a lot of steps. But again, just as with Laplace transforms, Fourier transforms also characterize the distributions. So I'm just going to state a theorem that is analogous to this long theorem that we just proved, but I'm not going to prove it, okay? It's too much time. And the ideas are, again, very similar. You just need to approximate using maybe trigonometric functions or this exponential type, complex exponential type functions. Anyway, so here's the theorem, and the name of the theorem is Fourier transform determines the distribution. Okay, so Fourier transform determines the distribution. Okay. So let x be a real valued random variable, and let nu be a measure on R with the Borel sigma algebra. So the following are equivalent. So just it's going to be the same statements repeated for this case. So x has distribution nu. F of x is given as fd nu for all positive measurable f. Well, f is on R now. We have the same formula for all bounded measurable f on R. We have the same formula for all continuous bounded continuous functions on the real line. And finally, we're going to write down a statement about the Fourier transform, not Laplace transform. And it is EIRX nu dx on the real line. Of course, this is a complex valued measurable function. We define its integral by the last step. Remember the construction of integral: indicators, simple positive functions, positive measurable functions, real valued functions. And the last step, which we did not talk about too much, is the complex valued function. So this is cosine Rx nu dx plus I times sine Rx nu dx. Okay, for all R in the real line. and the proof is omitted. Omitted. But its proof is quite similar. Indeed, just this big step, 5 to 4, is the difficult one, and it's the one which is going to change. The other steps, the other parts are all the same. Just 5 implies 4. For that, you need to use maybe another version of Stone-Weierstrass theorem. Not using polynomials, but maybe some other type of functions.